And as promised, I'm here for the first math video. All right, let's get into it. What are we talking about today? We're talking about linear maps. And for some context, this is a continuation of my series on linear algebra, which is the study of vectors, matrices, linear things. And we'll get into that term linear here in a second. If you want to see a little more holistic picture of what we've done so far, I recorded my last linear algebra video, again, like 3 years ago. So make sure to check that out. It was on linear independence, dependence, bases. So that would be some good context to have going into this video. But this is kind of still a new topic, all right? Linear maps. Okay, let's break down both of these words. Okay, let's start off with something simpler, maps, all right? All right, it's not the kind of map you're thinking. We're not talking about the map of either US or the map of China. No, we're actually talking about functions. So this is kind of a fancy word for, maybe actually this is a simpler word for function, okay? So, and hopefully going in, you know what a function is. If you don't know what a function is, that's okay. All right, a function is something that takes a value and sends it to another value, all right? One value sends it to another value. We can't have things like one value being sent to two different values, okay? That's illegal in the world of mathematics. Or at least it's not a function, all right? That's what we like about functions. It just takes one thing and sends it to another thing. And that's also called a map. And you can use the word map while describing a function because you can say one thing, let's say x, gets mapped to another thing, let's say y. Okay, but we need to understand like what are the values of x that we're sending to which values of y, you know what I mean? Because like, are we sending numbers to like numbers, or are we sending like zebras to elephants? Like, what are we doing exactly? So you need to define your set of things that you're mapping to, and you also need to define your set of things that are being mapped to. I don't know if English is Englishing there, but I digress. Let's move on. And so on that note, the way people usually write a function, a map, you'll usually see the word f, all right? F for function. And then you take f from like some set A to another set B. So that's the funky notation that you'll usually see, but it's actually pretty descriptive, all right? Because not only does it tell you how we're gonna write that function f, all right? But it also tells you the set that we're starting from, the set that we're ending from. So for example, you could have a function, something that we're quite used to, function from the real numbers to the real numbers, all right? So I don't know, like a really easy example of that is f of x, defined by f of x equals x. So it just takes any real number and sends it to itself. And we have a special name for that. That's the identity map, because an identity, it doesn't do anything. It just fixes something in place. And so this holds a special place in the hearts of mathematicians, because it's very simple. And in fact, it's also linear. And I think you guys can get behind that, right? Because if you've taken any basic pre-calculus, not even pre-calculus, pre-algebra class, then you know what a linear, what a line is, right? You know, like if you have your XY plane, you take a line that goes through the origin like this, for example. We all know this is y equals x. And in general, you can have a line in the form of y equals mx plus b, right? Where m is your slope. I feel like that's pretty common in the US, that it's taught that way. Mx plus b, okay? And we have y equals x, okay? Why do we like lines? All right, because what's nice about this is that every little bit we go in the x direction, remember, our slope is always the same for a line, anywhere you look, right? The whole point of a line is that, well, you have that slope in front of the x. That's your m, 1 times x. So in other words, what is slope? It's rise over run. So every run that you go, you know your rise is always going to be the same. And the reason mathematicians, people who apply math to the real world, like economists, finance bros, the reason they like math, the reason they like linear functions like this is because of that property. Because, for example, if you're looking at, and this is a stupid example, but if someone's making a salary, and they're making that, I don't know, like weekly, okay? Again, I haven't gotten a job yet, so bear with me. I haven't, taxes haven't started flooding in even though I'm 18, all right? But I digress. Anyway, back on track. People are getting a salary. Let's say they're getting that salary like every week, okay? Some certain amount of money every week, so per week. What's nice about linear functions is you can model that, because if you're getting the same amount of money every week, you can say, okay, so I know in 2 weeks, no matter which 2 weeks you're looking at, right? You made like double that amount of money. You know exactly how much money you've made based on the amount of time that has elapsed, all right? No matter when that time elapsed has taken place. Whereas if your money is modeled by some exponential function like this, I think we can all agree that's non-linear, okay? Then if you look at any interval of time of the same length, you see how that height changes. Like here, the further we go down, the more money we're gonna make in the same amount of time. So that's not really convenient. But that's why we like linear functions, all right? And that's where that second piece, linear, comes in. So I'm just gonna draw a line, all right? Linear. Okay, so that's kind of what a linear map is, but the goal of linear algebra is to kind of generalize that to higher dimensions. And in fact, different kinds of dimensions beyond the real numbers. I'm gonna erase all this. I'm gonna try to keep these videos also bite-sized. Running at 7 minutes. All right, I'm gonna try to keep it down to 10 minutes, but we'll see how that goes. So a linear map, let's come back to y equals x, all right? Let's actually do y equals 2x. I think we can agree that that's still linear. It's still a line, but with a different slope, 3. Well, all right, I'm gonna write this as f of x just to bring it back to our notation a little bit. And I want you to notice something. I'm gonna put what we just did into words or into mathematics. And we're just talking about how if you take x and you add any little bit of increment to it, let's call it y, or if you want, we can call it like delta x, and also say, okay, we can use y there, doesn't really matter, but any change in x, all right, I'm gonna call this x naught and call this, you know what, let's not be confusing, let's just stick with y. What I was trying to say is like, okay, that little bit of increment beyond x, but we're just gonna call that little bit y. So we're starting at x, we go a little bit y, then we know that that little bit that you go, that's what's nice about linear functions is that's gonna be, well, let's see, in this case, it's 3 times x plus y, because I'm just plugging in this into your x there, right? That's gonna be 3x plus 3y. Well, what's 3x? That's just our f of x, right? And what's 3y? That's our f of y. So again, what's happened here is that every time we go y, no matter what x we start at, right? We always go up by f of y, the same amount. It's based on y, not based on x, which is nice again, right? That's what it means to be linear. And funnily enough, we've actually just created the first property of what linear function is in general, and that's that for all x and y, f of x plus f of y equals, sorry, f of x plus y equals f of x plus, gosh darn it, plus f of y, all right? A little slow this morning, I haven't gotten my matcha in. 6'4", by the way, and I read feminist literature. Just send me now. Anyhow, that's our first property being linear, okay? That's really nice, okay? So we have this. What else do we have? This isn't actually enough because you could have functions like f of x equals 3x plus 1. All right, we call these linear, right? Like this is a line. So it would just be shifted up by 1, right? It would be the same thing that we have going here, but we're going up. We don't go through the origin anymore. in other words. But mathematicians like going through the origin. These functions, they wanted to build them so that they're really nice. They wanted this property that f of 0 equals 0. And so when that's violated, they call this an affine function. They don't call it linear because it's inconvenient. And we'll see why this result is very inconvenient later on when we work with bases and involving those in linear maps. But this is really nice, okay? This is not so nice because it doesn't go through the origin. And so what I'm trying to get at is a way to make that true, way to ensure that is if you say like f of x, let's say f of any constant times x is equal to that constant times f of x. Right? I know I'm just blabbering on, saying some words, but if you look at that, well, that means f of 0. If you think of c as 0, right? F of 0 times x equals 0 times f of x. And that's just 0, and this is just f of 0. Okay, so that gives us that property. But this also makes sense, right? Like, if we start at 0, no matter how much, like, let's look at f of x, for example. Maybe f of 2x, but let's stick with f of 3x. It's our favorite guy, 3x. Okay. I'm supposed to go through the origin, but my artistic skills obviously aren't up to par. You know how it is. No matter how much like you scale, and so if we're starting at like 1, for example, so 1 and that gets mapped to 3, all right? If you multiply 1 by like 3, all right, 3, then we expect that 3 to multiply out and get to 9. That's exactly what we're saying here, and that makes sense, right? Because if you plug in 3 times 3 times 1, that's just going to be 9 times 1. So you see how that constant multiplies out, and that's just 9, okay? All right, we're at 12 minutes. Great. So I just want to finish on the following note, which is just a summary of what we've already kind of come to. And my kind of goal for some of this is to not just state things out of the blue and kind of give you guys some intuition on like, why are we doing this? Because I feel like you guys deserve that. It's kind of stupid to just mention stuff out of the blue without like warranting an explanation. So linear map, a lot of the times people call linear map T, all right? You'll also see S. TS is so tough. Anyway, don't let the intrusive thoughts went out. But things like this, okay? And sometimes you'll see, like, instead of f of x, or instead of t of x, right? Again, f can be t. You could see something like this, but you could also see something like t times x. And that looks confusing, but that means the same thing as this. So in case you see that, that's what that means. I'll probably be using this just to avoid confusion. Okay, but a map T, all right, let's use T for now, from any set, let's just say, I don't know, right, A to B, sure. Then we call T linear if it satisfies these two properties. If we're gonna use for all, that means for all, okay? That little upside down A, talked about that in a previous video. For all X and Y in A, okay? For each one of those, no matter which two we choose, all right? We have the following, which we just talked about, T of Y. And then finally, for all X in A, we have T of, and every, I should say, remember we have fields in a vector space, okay? So a field is just the complex numbers. These are like sort of like constants. These are our constants. And we usually denote that in general by F. So F is a field and it satisfies, nice properties like everything has an additive inverse, almost everything has a multiplicative inverse, these kinds of things that we kind of take for granted sometimes with R. C also has those, okay? And so for all X in A and for all, let's say, constants in our field, then we know that T times Cx, T of Cx, you see, is C times T of X, okay? that's just what we've covered. And I just want to make one final note. Again, we're using arbitrary A and B. You know, A could be a higher dimension than just R. A could be like R to the power of like 5. Okay, this isn't like R to the 5th power. I shouldn't say it like that. But R5 is how you would describe it. It's 5 dimensions of the real numbers, okay? We live in R3, 3 dimensions, okay? So you can think about it like this. And in 3 dimensions, what's linear? We could look, to see something that's linear actually, you could look at a plane. I'm gonna leave it as an exercise to see, for you guys to find out why is a plane. So a plane again is just, think of your R2 plane, but you push it into R3 and you kind of like, you can like rotate it around, but it has to go through the origin. Why is that linear? Okay, I want you guys to think about that. Of course, lines in R3 are still linear, right? If they go through the origin. Again, point is, linear maps, they aren't just on the XY plane, they're everywhere, okay? And we're gonna talk more about the theory behind linear maps in the next video. I'll see you then.